You're whisking a sauce that has been thickening for minutes, glossy, pale, and behaving exactly as expected. You add one more spoonful of oil, and in a second, the entire structure collapses into a greasy yellow puddle. This breakdown shows the ratio of ingredients inside the bowl. Mayonnaise is overwhelmingly oil, typically around 80% by weight. The remaining 20% is water, provided by the lemon juice, vinegar, and the egg yolk. To hold these together, the sauce functions as a suspension. The oil is broken into millions of microscopic droplets, each one floating in a thin sea of water. Left alone, these oil droplets naturally want to merge. When two drops touch, they combine into a larger one, which is why oil and water usually sit in separate layers. Preventing that merger is a matter of microscopic structural engineering. The egg yolk provides the necessary stability. It is a chemical warehouse of fats and proteins containing specialized molecules that act on the borders between the oil and water. This model represents lecithin, an amphiphilic molecule. One end is attracted to water, while the other is attracted to oil. Whisking tears the oil into droplets. The lecithin molecules immediately move to these borders. Oil-loving tails dive in, water-loving heads stick out. This creates a protective shell. When two coated droplets bump together, those water-loving heads repel one another, causing the drops to bounce apart instead of merging. As you add more oil, you create more armored droplets. They crowd together and push against their neighbors, which is why the sauce feels thicker and stiffer as the whisking continues. Every spoonful of oil increases the density of these spheres, pushing the entire mixture toward a physical threshold. This diagram compares the packing limits of different objects. While rigid spheres leave gaps, oil droplets are squishy. They deform and flatten against each other to fill every available milliliter of volume. But the system fails at around 85% oil. At this point, the water between the droplets runs out. The lecithin coatings lose their environment and rupture, causing the droplets to collapse into a single pool of oil. Several factors can cause this collapse to happen prematurely. If oil is added too quickly, it creates droplets before the lecithin has time to coat them, leading to an immediate break. Temperature also plays a role. Cold ingredients move slowly, making it harder for the lecithin and proteins to reach and protect new surfaces in time. Finally, introducing free water that lacks these emulsifiers provides no molecular protection for the droplets, creating a weak point in the structure. Using these rules of molecular protection, consider how to fix a broken batch. Do you throw it out, add a fresh yolk to the broken bowl, or drip the broken puddle into a new yolk setup? The answer is C. A broken emulsion cannot be patched. It can only serve as the oil supply for a new structure. The rescue requires a clean bowl with a fresh yolk, a teaspoon of water, and a small amount of mustard. The mustard adds its own proteins to support the new lecithin, creating a robust environment. As the broken mayonnaise drips in, fresh molecules swarm and armor each incoming drop. Once the new emulsion thickens, you can add the remaining liquid. This graphic summarizes the 4 principles of a stable sauce. Match the temperatures, add oil slowly at the start, stay below the 80% oil limit, and restart the process if a break occurs. Shifting the focus to these molecular requirements allows you to anticipate when a sauce is reaching its limit and